Now we're dealing with another example of our stoichiometry problem, but in this situation, I give you values for both your reactants. So it starts out, it reads, how many grams of aluminum oxide can be used, or can be formed, excuse me. That's my theoretical yield from 100 grams of aluminum and 100 grams of oxygen gas. So I have my balanced chemical equation. And so I want to know how many grams of my aluminum oxide, that's my Al2O3, can be produced. The thing is, I have 100 grams of my aluminum and I also have 100 grams of oxygen. The problem is, I don't know who's my bread and who's my cheese. So what I'm going to do is I'm going to work them both through the actual roadmap. They both have a common location, different starting value. So both of them are going to start with mass. They're both are going to move to the moles of the aluminum oxide and then back out to mass of aluminum oxide using molar mass. So that's going to be the actual roadmap, and both are going to start this. The only thing is, I'm going to be starting over at mass for both of them. I'm going to do this roadmap twice. So in this situation, I'm going to start out first with my aluminum. Again, I want 100 grams from the actual problem. My first step, since I'm starting out with mass, my first step is going to be molar mass because I have to get back to the mole bridge. So I have to get down to the mole bridge. The mole bridge was used to actually cross the river and go from aluminum to aluminum oxide. So my grams have canceled out. Now I'm going to loop moles of aluminum. So now I see that I have 4 moles of aluminum. I got that from my balanced chemical equation, and I'm going to my Al2O3, which is 2 moles. Now what I could do with this ratio, if I wanted to, 2/4 is the same as 1/2. But now I'm on moles of aluminum oxide side. And then I go 1 mole of aluminum oxide, and I look up on the periodic table, the mass of 2 aluminums plus 3 oxygens weighs in at 101.96 grams. Now the rest is data entry, so it's 100 times 2 times 101.96 divided by 26.98 divided by 4 equals. What I see here is that my 100 grams of aluminum will be able to produce 189.0 grams of aluminum oxide. I'm not done yet because I don't know if that's my limiting reagent. I still don't know if that's my bread or my cheese. So I'm going to now do this exact same roadmap, but now with my oxygen. So I start out now with 100 grams of oxygen, which I got from my problem. That's my other reactant. I'm going to now use the molar mass of oxygen because I have to get the grams of oxygen down to moles of oxygen. Now I'm going to actually have a different ratio because I start out now with 3 moles of oxygen and I'm going to 2 moles of aluminum oxide. But since my final destination is the same, I can actually copy paste the molar mass of aluminum oxide. So I can actually bring down my 1 mole equals 101.96 grams. So my grams of oxygen cancel out, moles of oxygen cancel out, moles of aluminum oxide cancel out, and end up in grams of aluminum oxide. So I multiply across 100 times 2 times 101.96 divided by 32 divided by 3 equals. And what this tells me is that my 100 grams of oxygen can actually produce 212.4 grams of aluminum oxide. Now to figure out my limiting reagent, remember we'll go after the smaller amount. Just remember the bread gave us 4 sandwiches, the cheese gave us 6, we went for a lower amount. So we're going to go for a lower amount, which was a 189.0. You'll never get the 212. Why? Because your limiting reagent, aluminum, will run out. And that's the gasoline in your vehicle. Once it runs out, the reaction stops. Now the question is, how much my excess is actually remaining? So my excess, since my limiting reagent is aluminum, I know my excess is oxygen. What I do know is I started out with 100 grams. The thing is, I just don't know how much was used. So to figure out how much was used, once again, I start out with my limiting reagent. Because remember, once my aluminum runs out, not only does it limit how much aluminum oxide that you can actually form, but it also limits the amount of oxygen that you use. So I get my 100 grams, that's my limiting reagent, which I just determined. I'm going to use molar mass, which I've already done. We did copy paste, we did this above. That got me down to the mole bridge. Now I can cross the river. So now I'm going from 4 moles of aluminum to 3 moles of oxygen. And then I want to know my mass, so to figure out how much you use, I have to get out to mass, so I can subtract mass. So now I know 1 mole of oxygen equals 32.00 grams. Now I'll take that and multiply across 100 times 3 times 32, divided by 26.98, divided by 4 equals. And I realize that when my 100 grams of aluminum actually ran out, I had used only 88.95 grams. How I like to talk about it is money. You went into the store with $100 of oxygen, or auction went into the store with $100. Aluminum limited auction to only spending $88.95. So how much did auction have remaining? Had $11.10. But based on sig figs, we just say 11.1. And in reality, we're talking about grams. The next question asks, what student does a lab in which she makes 2.17 grams of lead 2 nitrate? So right when I know she makes it, that means it's her actual yield. She actually carried out the lab. That's actual yield. From her limiting reagent, she calculated. Key thing, from limiting reagents calculated. That's what we just did that. That means my 2.55 is the theoretical yield. I want you then to determine theoretical yield, actual yield, percent yield, absolute error, and relative error. Well, we've already figured out theoretical yield was my 2.55. My 2.17 was my actual yield, what she actually got. To get percent yield, she takes what she got, her score, divided by the total, which was 2.55, multiplied by 100 because you want to make it to a percent. Now I won't run you through doing absolute error, nor will I ask you to do relative error, but we see that relative error, or your percent error, is 15%. We then see if we were to take my 85% yield, 85.1, just round it back to 85, that's what I got as a yield, then how far away was I from a perfect score of 100? I was actually my percent error of 15%. Therefore, once you know your percent yield, you can also figure out your percent error, because the sum of the two must add up to 100%. Last problem we're going to go through is we have a sample again of hydrazine. And now with this situation, here's my balanced chemical equation. And I realize I have 100 grams of hydrazine and 280 grams of oxygen. So when this was actually burned in laboratory, 97.2 grams of water were actually formed. That is my actual yield when it was actually carried out. So that's my actual yield of water. That's where I'm going then. I need my theoretical yield. I said percent yield, but I know to get my percent, I need my theoretical yield. What's the maximum? Where am I going? Well, my actual yield is of water, so I need my theoretical yield of water, right? You're not going to take your score from unit 3 and divide it by the maximum from unit 1. You just don't do that. That doesn't give you the correct percent. So you're going to take your score from test 3 divided by the total from test 3. So if I have the actual yield of 97.2 grams of water, I also am going to want to solve for the theoretical yield of water. So then I realize my hydrazine and my oxygen are both going to go to water. The problem is I don't know who's my bread and who's my cheese. So like we've always seen, we're going to run these both through the roadmap. So there's my 100 grams of hydrazine from the problem. The first step, always when I start out with mass, is molar mass. And so I have to get down to the mole. And so I looked up I added up 2 moles of nitrogens and 4 hydrogens. I got 32.06 grams per mole. My grams cancel out and I'm in moles. Now I'm going from 1 mole of hydrazine, I got that from the periodic table, to every 2 moles of water. Just got that not from the periodic table, from my balanced chemical equation. So 1 mole of hydrazine to every 2 moles of oxygen, those are the 2 coefficients from the balanced chemical equation. Now I just crossed the river and I'm on water side. The last thing I need is a molar mass of water, which you've memorized, many of you, 18.02 grams per every 1 mole. My grams cancel out, moles cancel out, moles of water cancel out, and end up in grams of water. All I'm going to do is multiply across 100 times 2 times 18.02 divided by 32.06 equals. So it tells me my 100 grams of hydrazine will produce 112.4 grams of water. I'm not done though. I still don't know if that was my bread or my cheese. I don't know yet. So I have to do the exact same thing with my 280 grams of oxygen. Again, I got the 280 grams from the problem. Use a molar mass of oxygen, which is it's 2 oxygens, so 16 times 2 is 32 grams per mole. My grams cancel out and in per moles. Now I'm going to go from, looking at my balanced chemical equation, I'm going to go from 3 moles of oxygen to 2 moles of water. And then since I've already done molar mass, copy paste, I have the molar mass of water. Now again, I'm going to take my 280 times 2 times 18.02, divide by 32, divide by 3 gives me 105.1 grams of water. So what's my theoretical yield? It's the lower of the two amounts. You'll never make it to 112. You're going to only get stopped at 105. Why? Because your limiting reagent oxygen, your 280 grams of oxygen is going to run out. So 105.1 is your theoretical yield. That's the maximum score you could have gotten the test. So to get percent yield, all you're going to do is you're going to take your score, 97.2, divided by 105.1 times 100 gives you 92.5%. What was your percent error? In other words, how far away were you from 100%? Yes, you were 7.5% error. That's how far away you were from a perfect score.